maybe they can see both boards. Hey, that's gonna work. I'm off center, but who cares about me? As long as they can see the boards. Yeah, that's all right. Okay. When we left this morning, we talked about the three qualities of electricity. Give me one quality of electricity, Anton. Current. Current, good. It's measured in what? Current is measured in what? Amperes. Okay, so current. What's another attribute of electricity, Matthias? Voltage, good. Measured in, Devante? Measured in voltage, measured in volts. Okay, we got current, we got voltage. The third portion of electricity, Alessandra. Resistance measured in ohms. Good. We're going to spend a lot of time talking about resistance today, whether you resist or not. Let's see what I got. Let's see what I got for folks at home. I got a bunch of folks now. Where was everybody first period? I missed you all. These people.
They all sleep.
Okay, but I'm glad you're all here now. So hello to Hannah. Hannah was here both hours. She's on top of things. Aslan. I got Kai. I got Aaron. And Ayala. I got Ethan. And I got, okay, good. Whoa. Felix, could you prop that door open, please, with a chair? I'd appreciate it. That will bang shut all the time. Okay. So, folks that were not here this morning, you'll have to go and watch the video and review a bit. So we're going to start up with where we left off, which is about circuits. And today, everybody here, we're going to solve a circuit. Okay? So, solving circuits. We'll see how far you got with your teacher last year, but it's an essential in electricity. Okay. We need to talk about resistance again for a second. So here's a wire or a lead, and we said if I got flowing electricity, Isaac, flowing electricity, I got what moving through my wire?
Electron.
Thank you. So I'm going to draw some. I'm going to have it moving this way. And we said what this morning? That what's providing the resistance as the electrons move? Vanessa. Friction. Yeah, with what? With the atoms in the wire. So friction as they move through the atoms of the wire, the atoms of copper or whatever it happens to be. Good. What could I do to reduce the resistance? What could I change with this drawing? There's more than one answer. What could I do to reduce the resistance? Isaiah, can you guess one thing?
Take away some.
Exactly. So that would be cutting down on the amount of flowing through.
Cutting down the
Amount of electrons, but what do we call it? We're reducing the what then of the circuit?
what?
It's in amps, but it would be then, Jack, the amount of current. Okay, so I'm cutting down the current. So that'd be one way, Isaiah, right? So less resistance if I have less current. What's another thing I could change about the picture? Another thing, Anton? I could make a bigger wire. So if I have a big cable like this, there's a lot less resistance than if I have a very thin wire. Okay, makes sense, right? It'd be like having a wider S-bond or something. Okay, more and more things can fit through without there being, so there'd be less friction that way. Isaac.
If you reduce the length of the wire.
Good. So the other thing I could do is extend the length of the wire, and if I do that, That
Does
actually
it
does
increase,
what?
that'd be more.
Yeah, Leo, what?
I was thinking that'd be more resistance.
That'd be more
Shorter with
resistance.
the length.
So if I wanted
I
less
see.
resistance, I could shrink the length of the wire. So there's less that they have to go through. So just get you thinking about resistance a little bit. I don't know if any of you tested these last year, resistors. I know Devante did because we did it, right? The resistors, we had to find the resistance in ohms of different resistors in our circuits. Anybody else do that with your teacher? You've done it.
Yeah.
Okay. Resistors are in the backs of all sorts of stuff you have. I'm not asking you to rip your phone apart, but if you have something you can see the back of a calculator, phone, laptop, you're going to see that there's little tiny things with little stripes on them. You ever seen the little electrical things? Those are resistors. And the reason they're there is they need to then adjust the amount of getting through, yeah, current getting through, because different parts of your handy need different parts of current. And your laptop is even more sensitive. So there's lots and lots of resistors in your electronic gizmos. Lots and lots. Let's see if anybody else showed up here. I've got another person. I got Isabella. What about you? You're here. That's what about you. I'm glad you're here. Okay, so I got my Isabella. Let's see if I get anybody else. I think I got everybody there. Yeah. No, never mind. Okay. All right. And Ethan's right. He said current as well. Thank you. Good. Yeah. I'm sorry, Isabella. I didn't see your name up there. Okay. I gotta apologize to my screen. Okay, so that's about resistance. Now let's solve a circuit. A series circuit. I don't know if we got that far this morning. How does it look as a shape? A series circuit, Devante? It'd be just as clear. Okay, so here's a power source. And in this series circuit, I'm going to put 3 resistors. What was again the symbol? The symbol for resistor that we had this morning? It was, Felix?
The zigzag?
The zigzag. So here we go. Let's put 3 zigzags here. Here we go. You can tell I'm not the best at drawing these, but I'll do my best to. Okay, so I've got 3 resistors. Now I'm going to put some values on them for us, okay? To make life a little more interesting. So we're going to say 10. What do we measure resistance in again? What sort of label? 10, Alexandra? Omega, ohms, right. So I'm going to say 10 ohms, 5 ohms, and 5 ohms. And I'm going to pick an amount of voltage for my power source. So you can just write this up here too. Let's say we've got 60 volts. We're going to answer some questions about this. And, oh, you don't have that tool yet. Well, we better give you that tool. Or you might have had it, but you might have forgotten it since last year. Squiggly line, exactly. Exactly, Ethan. Okay, so the resistance, we got to get the current. Now, there's a computer's going to lose me, sorry. There's a relation between the 3 things, current, voltage, and resistance. It's called Ohm's law. So I better write that with the first. Ohm's law, which says the more current, the more voltage the relation, or we're going to say slope, is the resistance. Let me show you that on a little tiny graph. We will come back and finish this, but I realize that we don't have the tool yet because we didn't review it. Okay, so Ohm's law for folks at home, if you can't read that very well. The more current, the more voltage. The relation slope is the resistance. Here's what I mean by that. If I got like we did last year, like I think Ethan and Devontae both did this with me last year. I got voltage over here. In volts, I got current and amps, and I get like a direct line. It doesn't have to be a 45 degrees, but whatever it is, I get a linear relationship. Almost linear line. I never do this. The slope of that line, remember that slope in math class, diagram? The slope is equal to the resistance. That's what Ohm's law says in symbols, okay? What does that mean for you and I? What it means for you and I is to get the resistance, I take the, well, what would it be, math class slope? Rise over run. What letters does it end up being here? Rise over run. Vanessa? Yeah, good. B, like the rise, right? Over, what'd you say? A, yes, although current we use a different letter for the variable. You remember what, it's measured in amperes, but I. So that comes right from the graph. So this is essentially Ohm's law. But to be honest, most people remember a different way. Either Devontae or Ethan, do you guys remember from last year how to remember Ohm's law? How do you remember Ohm's law? Ooh, I'm glad I asked. Do you remember that, Devontae? Shall I give you a hint? Ethan too? Twinkle, twinkle, little star.
It was like the vulture, the opposite turtle.
I don't know what teacher that was, but it wasn't me. I don't do vultures and turtles. No.
And it was someone,
I like it, but no. Oh, it could be. Yeah, okay. Aslan says, yeah, okay, yeah. All right. It's like this. Twinkle, twinkle, little star. V is equal to IR. That's how you're going to remember it the rest of your life. Twinkle, twinkle, little star. Everybody say that. Twinkle, twinkle, little star.
Yeah.
Oh, your son's so enthused. Oh my gosh. You really will remember it that way, okay? And here's the other thing to do to remember it. Some of you are familiar with this idea. Anytime in physics or chem, when I got one variable equal to 2 when you multiply them, I can do what's called a triangle. Who knows what I'm talking about? How can I build a triangle for this thing? Somebody tell me how to do it. You remember how to do it now? Isaac?
So pretty much you put the variables in so that like the half of the triangle is kind of like a division sign.
Yeah, good. So what goes on top?
B.
Yeah, it's like division. In other words, let's say Isaac wants to solve for I, then it covers up I, and the equation would be
B over R.
V over R. You can do this with anything. If I want the resistance, it's V over I, but we already knew that. That's from Ohm's law. If I want V equals I times R. So the bottoms are just multiplied together. Again, you can do that for any equation that's got 3 parts that are related like that. So it's kind of a cool tool.
Oh.
I know. Okay, so here we go.
Don't do that. Stop.
It's time to solve this thing. Here we go. I'm gonna ask you a bunch of questions. So,
Hey, no, stop. No.
hey, folks, just relax. You're not maybe taking, you're done cracking. Thank you. Okay. So, A, I want you to find the total resistance B,
It's only two.
you're gonna find the total current. C, you're gonna find the voltage. In
Oh, no.
each resistor. And I'm gonna help you do it. Okay, so for the first one. Yeah, I agree, Ethan, that would make sense too. Ethan says it should be twinkle, twinkle, little triangle. Yeah, well, kind of. Okay, so. For the first one, total resistance, A. We're gonna do one of these, by the way, and then you're gonna do one on your own here in a little bit. And I know that clock is wrong, so I have less time than I think. For A, to get the total resistance, let's see if Simon remembers. If this is a series circuit, which it is, series circuit, and I'm gonna say this is like resistor number 1, resistor number 2, resistor number 3. How do I get the total resistance? What do I do with the numbers, Vanessa? I add them up. So to get the total resistance, I'm going to give it an equation first. If it's a series, like this one is, I take the resistance at 1, plus 2, plus 3, plus however many I got. Here I only got 3, don't I? So 1, 2, 3. Okay, so who's seeing what I'm doing? What numbers am I adding together here? Just so I know you're following. Leah, what am I adding together?
10, 5, and 5, so 20.
Okay. 10 ohms plus 5 ohms, because we need labels, plus 5 ohms. And he's right. So the RT, the total current, or total resistance is 20 ohms. As a reminder, Achtung, for my German colleagues as well as my American colleagues, you gotta have labels on the numbers. So don't just put a bunch of numbers. Labels, and then you'll get actually all the points. Let's go to 2. So 1 is done already. Total current. And again, current, Felix, is which letter again?
So it's on.
Okay, so, yeah, so what's the equation I use then? If I want to solve for I, like Isaiah, then it's equal to what over what? Use the triangle, Isaiah? V over
R.
R. You got it, right? V over R. Beautiful. Okay, throw me the numbers in, Isaiah. What do we got for a voltage on my little circuit?
60.
And then the total, sorry, this is the total now
Oh, that's 20.
that we got from
40.
Leo just a minute ago. So you're dividing 60 divided by 20. I got too many equal signs. That looks sloppy. 3 what? And it's not watt. 3 what? Person? Amps. Yeah. Is that a little or a lot of current? Yeah, it's a lot, isn't it? Yeah. You can, the human body, guys, you can feel, do we do this already? How much does it take till you can feel it? How many amps? 0.01. You can feel 0.01. How much until you get a shock and it kind of hurts? Yeah, 0.03.
How much is like a taser?
Something that goes through enough to disrupt your heart, 0.15 amps. So that, folks, that's a lot of amps. That's enough to not good. Okay, good. Exactly, Aaron. Righto. Good. Let's do the last part. Oh, and by the way, let's get back to my circuit. We did this morning, but let's just make sure we can still do it. Remind me, which way the electrons go in here? Alexandra, I want to put some more arrows. Okay, so I'm gonna do that. Everybody at home do that as well. Look at what we found so far. We're not done, I know, but we found that the total current is 3 amps. Well, what's the current here? Or here? Or here? Or here? Leo.
Well, you just figure out without the resistance. So, for example, after the first one will be 60/10, so 6 amps, no?
Separate question. You might know, but I'll come back to you, Isaac, I promise. How many pathways do the electrons have in this circuit? In essence, 1. And if the total current going through is 3 amps, Isaac?
I think it's always the same, right?
3 amps, 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 3 amps. Yeah, it's the same everywhere because there's only one pathway. So it turns out it's 3 amps everywhere.
Isn't it different in the parallel circuit?
It is. So what I'm doing, okay, what I'm doing with you today is we're doing a series circuit, and tomorrow we'll finish up with a parallel circuit, okay? Everything today is only for a series if it's like a box, okay? All right, so the current is always the same. In symbols, here's how you show that. R1 equals R2, no, wait a minute. I'm sleeping, sorry. I1. So here's how physicists show this. So they're all the same. Right?
Question voltage? So what is that?
Yeah, we're not done yet. We're gonna get to C here in a second.
Okay. Yeah,
Gentlemen, I know it's 8th period, but don't make me kill you. No, at the end of the day, all right? Okay, stay with me. I can move you around if I need to as well, but I'd rather not do that. Okay, so questions so far. So in a series circuit, the current's the same everywhere. The total resistance, I just add them up. And we use twinkle, twinkle, little star, B equals IR, solve for I, and we figured out the current for the whole thing. Let's do the voltage. The voltage is not the same. How many of you have ever had like a flashlight that's pretty long, and what do you got to do with the batteries you put in? What do you got to do that? It's like a long flashlight. I got to put in batteries. What do I got to do with those batteries? Isaac?
In like plus and minus side?
Yeah.
Okay. So you have to like organize them so one battery goes plus up here, and the other one's down here, like opposite kind of.
Yeah. And what do I do once I get those batteries in if I want to get the total voltage? Can you guess? I could use a voltmeter, but I could just do what? Look on the batteries and do what with the numbers? Let's say I got 3 batteries for each of them. Add them up. So if I got 3 voltages, they all add up. Here's what this means for you and I. The voltage going through this one, and this one is not the same. All right? Think of this being, remember, voltage is the push of the electron. So think of it being like this. I got a waterfall. It's got one part to go through, another part to go through, and another part to go through. 1, 2, 3 resistors. So what I got to do is I got to find the resistance, I got to find the voltage at each resistor, and then we'll get from there. Okay, so I'm going to erase this because I need the space here, and we're going to do C right now. Stay with me, and let's get the voltage in each resistor. So I want this one. I want the voltage through number 1. Okay, go to your triangle. B equals what? What I have for letters on the other side, Alessandra?
I times R1.
Yeah, good. So she knows because now I want just the voltage in that one resistor. I don't want the total. I just want the one at R1. Okay, Go over and throw some numbers in, Corsine. What's my current and what's my R1 resistor value?
First is, 20 ohms.
Yeah, not ohms, 20. No, the current? No, we found, I don't think it was that much. We found it in part
Oh, no, that's
B,
the resistance, 3 amps, sorry.
3 amps. Everybody find that in part B, 3 amps? Okay. And then Alexander says resistor 1. That's which one, Corsine?
10 ohms.
That's the 10 ohm one.
No, the 5.
No, it's
You're right, it's the 5. It's the 5. I labeled them over here, folks. So I just forgot my own labels. Good. Corsine, you want to continue? Then just multiply it out. I'd get how many volts? Yeah. That'll be the same as for which other resistor? Which other one? Did I answer? The second one, why? They're the same one. So can I just also say that's equal to V2? Is also that. Same numbers, right? Let's do V3. So I got V3 is my current times R3. And Isaiah, help me throw in the numbers.
So V3 equals
My current was from part B, how much again?
20.
No, that was resistance. 3 amps. Good. And what's my resistor 3, Isaiah?
No.
No, it's over there. Which one's number 3?
10.
10. 10 what?
10
10 ohms. Good. 3 times 10. 3 times 10. Probably 30 what? 30 volts. Look at our answers. Somebody tell me how you know that we did it correctly. Look at those 3 answers. And I'm ignoring my folks at home. Let's see if somebody can tell me there too. The right is a little blurry because you're further away. I'll try and get that over. You guys can see. Hopefully that helps a little. Sorry, folks. So I've got V1 is 15 amps, V2 is 15, V3 was 30. I know I did it right good. Alexander, why?
Because R1 and R2 are both 5, which is a half of 10. And the answer for V1 and V2
Oh.
both also the half of.
Okay, you're right. That's one reason, but there's another reason too. That's true, but Devontae also why? Yeah. Which is the total I gave you, wasn't it? Look at that. I gave you 60, and Devontae's right. Add these suckers up, and lo and behold, I get 60 volts. And it better work that way every time. Sometimes with a little rounding, it may be off by like a point one or something, but pretty much it better add up to the total. Good. I'm going to have you try one, all of you, and folks at home in just a little bit. Question first, Isaac, a comment?
So I have a question about the resistors.
Yeah.
According to the equation that we just did, essentially, the more ohms the resistor has, the less resistant it is,
No.
because the voltage came out to be higher.
Yeah. Okay, let's think about that. It's a really good question from Isaac. Here you go. If I had 10 ohms and I got 3 amps going through it, why does the voltage got to be higher? That's a lot of resistance. What's the voltage mean I got to do with those electrons there? Felix?
Maybe in order to keep the amp the same, it has to be a little more voltage.
Because I got to do what with the electrons?
Well, through.
Push them through. And do I got more or less resistance here, Felix?
More.
More. So that means I got to have more push. That's more voltage. Yeah, that kind of makes sense, right? Here I got less resistance. So do I have to push as much? No, it's easier. Oh, it's only 15 volts of pushing. Remember, that's the amount of electron push I got, change in energy. Makes sense, right? Let's go ahead and see if we can You're welcome. Let's go ahead and try one ourselves, okay? Here we go. I'll try and keep the numbers pretty easy, but if you need to use your phone for a calculator, you may do so. Okay, your turn. Same three questions. New circuit. I'll do it in black so folks at home can see a little easier as well. Okay, so boom. Yeah, so boom. And let's make Germany, we'll make this 220 volts. That's our household voltage Germany. Let's make these, I don't know, 5 ohms, 15 ohms, 20 ohms. And anything else you need? No, that's all you need. Let's see if you can do it now. So find the total resistance, find the total current, and find the voltage in each resistor. And let me make sure folks at home can see that as well. I'm going to move you over, folks at home. And hopefully you can see that. Okay, we'll give you a few minutes and then I'll have somebody, hopefully we'll finish up and we can put some parts on the board, all right? Look at what I did, you're going to do something pretty similar. I'm told 220 volts, yeah? How many of you did this last year? Kind of remember doing this a little bit? A couple of you maybe, not everybody, the ones that we did, right?
Yeah, I think I think that the turbo was different from 8th grade.
8th grade, okay, yep, okay. Okay, so folks at home try it as well. We're gonna have people help me. A, G, and the physics way is like I did, right? Formula, numbers with labels, answer. Part one, third, conclusion. All right, extra kudos if you put a label on each number. They need labels, right? 5 what? Fish, 5 chickens? No. 5 what? 4 what? 10 what? Ah, good. Okay, let's have some folks put them up there. Can you do Matthews part A first? Part B. Part, yep, see that? Let's give a second, I'm gonna finish up. Matthews, put the final answer there underneath the curve. And I know on C, you'll have to round them, like Anton's doing. The rounded values, when you add them, they should get pretty close to the total. We'll check it together. Came out exact, but that's rounded. It is, what's fine?
No.
5 times 5 is 25.
The tenth place,
Use the calculator and it was fine.
Yeah,
It's not.
never mind. If I have you next year, I'll teach you how to round, but, okay. So we'll worry about that some other time.
I don't know how.
Okay, total resistance, looks good. The only thing, if this was a quiz or test, I would want you to put the formula first. I know, but it's what we do in physics, okay? Again, my German colleagues do this too. So, there's the formula, Matthias has put the labels on each one, good job. Total 40 and ohms is the right label. Let's look at the second one. We got a nice formula from Alessandra. She's put in the values with their labels, 220 volts, 40 ohms from part A, 5.5 amps. Check Rooney. Check your labels, make sure they're the same as Alessandra's. Good, and 5.5 amps. Folks at home had that as well. Thank you, Ethan and Aaron. Soupy. Let's look at the third one. The only thing I don't have is a label here. So back to Anton. Shame on me, I meant to number these. So these would be like 1, 2, 3. Is that the way you did them, Anton? Is that your order? Okay, so I'm gonna call that not R1, B1, B2, B3. And for each of those, you use the same formula, right? Which one? Twinkle, twinkle, little star. 5 times out. So B is equal to 5 times out.
Couldn't we also multiply the first answer times 3?
Yes. Yeah, as it turns out you could. So, the other way you can do is, here, Corsin, What if I get the first two answers? What's another way to get the third one without doing this method? Yeah, and subtract from 220. It's another way to get it, okay? Estimate, what do we got? 27, 82, 110. Does that look like it's gonna add to 220?
119.
It doesn't. There you go, beautiful. So it should add, with rounding, it should add up to about 120. Looks good, people. Questions from all of you? Then, to end the hour, let's just review what we'll start next time, which is parallel. So draw me a parallel circuit in the air. What's a parallel circuit gonna look like? Okay, Vanessa, you're on.
I remember that. It's like a normal line and there's a line. It's like another line.
Okay, another line cutting through the middle. You can do it that way. Give me another way to draw it. Another way to draw it. Devontae?
Well, you can have basically one square and then.
Just draw.
one square under it, yeah.
And then you can put what through it. What sorts of lines? What are those in math class? Parallel lines. Okay, so long as you have both UN and so long as you both have parallel lines, you're fine. Question for folks at home too. See this sort of diagram? This is a series circuit. Why don't we wire our houses in this sort of circuit? Looks okay to me. What's wrong with it? Why don't you, is your house and apartment, why is it not wired with this one? Leo.
Well, I guess because if anything malfunctions the entire circuit collapses.
Okay, what if this resistor goes out? You're, you know what? Okay? Yeah, all the power dies. You don't get anything. Or what about to turn on your fridge? What would you have to do? Everything in the whole apartment. I have to turn on the blender, the fridge, the lights, whatever, okay, to make everything go. So we don't use series, we use what?
Parallel.
Parallel, good. Can we put up all the chairs, please? Thank you, folks at home. See you. Some of you, I'll see you in 2 weeks. Actually, I won't see the other group at all. I'm sorry to say. I'll see you guys in 2 weeks, right? Yes. I'll still see you tomorrow. That's fine. Thanks, Christian. We still got one more class tomorrow. Thanks, everybody. Bye-bye. Bye, folks at home. Thank you. Bye-bye.